Welcome to example 6 on page 130. This is a really cool example, and it's going to put together, we're going to use a lot of the skills that we learned in this section so far. So we want to find a power series expansion for f of x equal to the arctangent of x about a equals 0. And we also want to find the interval in which the series converges. So we want to find the interval of convergence. Okay. Well, you may look at this and think, arctangent of x, do I need to go back to Taylor series? Do I have to find integrals? Do I have to find derivatives and do all that work to find the power series expansion for arctangent x? Actually, you don't. We can use the methods of this section to come up with the power series expansion for arctangent x. What do you remember about arctangent x? I hope you remember the derivative of it. So the derivative of arctangent of x is equal to 1 over 1 plus x squared. And when you see that, I hope you're thinking, ooh, hey, 1 over 1 plus x squared, that looks a lot like 1 over 1 minus x, and we know the power series expansion of 1 over 1 minus x, and we've used it a bunch of times now. That is 1 plus x squared plus x cubed, and so on. And we also know the interval of convergence for this. This is true from -1 to 1. Now, we've done a few examples. We can rewrite 1 over 1 plus x squared as 1 over 1 minus x squared, and substitute minus x squared in for x in our known power series. So this becomes 1 plus minus x squared plus minus x squared squared plus minus x squared cubed, and so on. And when you multiply this out, you get a nice alternating series, 1 minus x squared plus x to the 4th minus x to the 6th. And even without having written out more terms, we can see the pattern. It's alternating, and we have all the even powers of x. So we have plus x to the 8th minus x to the 10th, and so on, going on forever. And this should be valid when -1 is less than minus x squared is less than 1. Okay, let's look at that interval of convergence a little bit more. We can manipulate that, multiply all three parts by -1. That gives us a 1 is greater than x squared is greater than -1, which, okay, we can just rewrite it in the other order. We have -1 less than x squared less than 1. But when is x squared between -1 and 1? That is really true when x is between -1 and 1. You can convince yourself that that is true. When you have a number between -1 and 1, the square is also between -1 and 1. And if you have a number that is bigger than 1, then the square is bigger than 1. All right, so we have the interval of convergence for the derivative of arctangent. Well, that's cool. And we have the power series and the interval of convergence for the derivative of arctangent. How do we go from a derivative to the actual function? We integrate, exactly. So the arctangent of x is the integral of 1 over 1 plus x squared dx. But we have this nice theorem that tells us that we can, instead of integrating a function, we can integrate its power series. And so let me replace 1 over 1 plus x squared with its power series. I think going up to x to the 10th shows the pattern. And we are pretty good at integrating by now. So we're going to write the arbitrary constant first, and then the integral of 1 is x. The integral of minus x squared is minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9. We still have an alternating series that picks up all the odd powers of x and then has that same odd power in the denominator. Now, what are we going to do with this c right here? We want to know what arctangent of x is equal to, and we can't have an arbitrary constant in there. So fortunately, we know the arctangent of 0. We know that the arctangent of 0 is 0. And we can use that to find our value of c. So we have c plus 0 minus 0 plus 0 and so on. That means that c has to be 0 as well for this equation to be true. And so we get arctangent of x is equal to x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9. We have the power series expansion. And if you like finding patterns and writing down this series in sigma notation, we can do that. N goes from 0 to infinity. And what do we have? We have an alternating series. So we have minus 1 to the n. And then we are picking up all the odd powers of x. We have 1, we have 3, we have 5, we have 7, we have 9. So we can write that as x to the 2n plus 1. And what do we have in the denominator? That same number, that same odd number, 2n plus 1. So we can also write this down in sigma notation. So a word about the interval of convergence. Because of the power series integration and differentiation theorem, we know that we can do this integration, and we also know that we are keeping the interval of convergence. So we can say that this power series expansion is valid for minus 1 less than x less than 1. Okay, this problem also has a part B. Let's move on to part B, and I'm gonna keep my power series. Well, actually I don't. We have to write it down again. New page. So part B says use P5, so the 5th degree polynomial from the series that we just expanded to approximate the value of the arctangent of 5, and compare your approximation with the value your calculator gives for arctangent of 0.5. Okay. Let's write down P5 of x. We need everything up to the 5th degree term. So we have x, then we have minus x cubed over 3, and then we have plus x to the 5th over 5. That's what we wanted. Okay, so this is the 5th degree approximation for the arctangent. So if we want to know what is the arctangent of 0.5, we can plug 0.5 into our power series expansion. So we have 0.5 minus 0.5 cubed over 3 plus 0.5 to the 5th over 5. And that is, when you plug this into your calculator, that's approximately 0.4646. So this is our approximation of the arctangent of 0.5. The calculator punch it into your calculator. Make sure you're in radians. The arctangent of 0.5 is, drumroll, 0.4636. That is not a bad approximation. We actually picked up the first two digits with just a fifth degree power series expansion. And so this gives you a little glimpse in why power series are useful. You can use them to approximate values of functions that are described as sine, cosine, e to the x, these special functions. And your calculator might be doing just what we were doing, or Mathematica or some other software when they are computing e to the 0.7 or the arctangent of 0.5, they might be just plugging those values into a power series expansion with a certain number of terms. So this is how power series can be used.